Continuing to the next few examples. We can use either substitution or elimination. So it looks like this next one, elimination would be pretty good because we can multiply the top by -2, and that should eliminate the x's for us. If we look closely, it might actually eliminate the y's too, which is something that we would like to look at anyway. So equals 16. In the bottom, we got 6x minus 8y equals -12. We go ahead and combine like terms, and we get 0 is equal to 4. Well, as we all know, 0 does not equal 4, so when we come up with something that is false, it's no solution, which means that these lines are parallel. Next one, this one looks like it's set up nicely for substitution, so let's go ahead and do substitution. It's already solved for y, so let's go ahead and plug this in for y, which gives us 4x plus 6 times y, which is -2/3 x plus 3, plus 2, equals 12. We will distribute. So when we distribute, we get -4x, 2/3 of 6 is 4, plus 12 equals 12. We go to solve. Well, these are like terms, so this is 0 plus 12 equals 12. Well, that is a true statement. It's always true. So if it's always true, there's an infinite number of solutions. And if you think about the graph of this, this means that these are actually the same line. And so what we do, our answer is the equation of the line. We could use either line, I suppose, but the better one is to use the one in slope-intercept form. So our answer is y equals -2/3 x plus 2. And now that we know it's the same line, another thing you could do, that's our answer. So we're done the question. We've solved it. But we could put this one in slope-intercept form, and we would see, so we'd subtract 4x from both sides and divide both sides by 6. So we get y equals -4, 6x. So we're dividing both sides by 6 plus 2, which is -2/3 x plus 2, exact same equation. All right, we get to the next example. These usually take a little bit longer because it's 3 equations with 3 variables. Our goal here, so listen close, our goal here is to take 2 pairs, so 2 pairs, one pair then another pair of equations, and we want to eliminate the same variable each time. Now, it doesn't matter which variable you eliminate, but if you eliminate z's when you take your first pair, you need to eliminate z's when you take your second pair. If you eliminate x's the first time, you want to eliminate x's the second time. So you just kind of choose which one you want to do or which works easiest. Honestly, with this one, you could eliminate x, y, or z. So I'm just going to go ahead and eliminate the y's. Because I see I have a -y here, I can multiply equation 1 by 2 and add it to the second equation to eliminate. And then my second pair, I can take 1 with 3 and eliminate the y. So the first 2 equations, say A, B, and C. So equations A and B, I'll show all the work here. As you get better, you probably can kind of think ahead a little bit. Just make sure you copy all of your symbols correctly. If you mess on this, it's a real shame to mess up on this because you make one little mistake and it messes everything up. So we're going to multiply the top by 2. And that gives us 4x minus 2y plus 3z equals 14. The bottom we didn't do anything to, so that's x plus 2y minus 4z equals negative 19. We can combine those, and our goal was to eliminate, so those eliminate. We get 5x minus z equals negative 5. Uh-oh, I made a mistake. It's good we caught it already. When I distributed this 2, I did not distribute it to 3, so this should have been 6z. And so we have 6z minus 4z is 2z. Okay. Now we're going to take equations A and C. We could do B and C, but I'm just going to go ahead and do A and C, and I'm going to eliminate y again. Because I eliminated y on the first one, I must eliminate the y on the second one. So we'll take our first equation, 2x minus y plus 3z equals 7. And our third equation, negative 3x plus 4y minus z equals 12. All right, this time I'm going to multiply my top equation by 4. Make sure I remember to distribute the 4 to each term this time. So this is 8x minus 4y plus 12z equals 28. And the bottom equation we're keeping the same because we will be able to eliminate the y's. Now we can combine those, and we get 5x, this eliminates, plus 11z equals 40. And now what we're going to do, now that we eliminated the y's twice, we're going to go ahead and take our two equations and solve those. So we have 5x plus 2z equals negative 5, and 5x plus 11z equals 40. Looks like I can just subtract these. So let's do that. Let's just go ahead and subtract. So we're going to do the upper one minus the lower one. So 5x minus 5x is 0. 2z minus 11z is negative 9z. And negative 5 minus 40 is negative 45. Dividing both sides by negative 9, we get z equals 5. All right, so we got our z. Now let's take that and plug it into one of these two equations, which is really these highlighted ones as well. Doesn't really matter which one. Let's put it in the first one, this one here. So we have 5x plus 2z, we just found z was equal to 5, is equal to negative 5. We'll go ahead and subtract 10 from both sides because 2 times 5 is 10. And we have 5x equals negative 15, which means x equals negative 3. And now what we do is we take z and we take x and we plug it into one of our 3 originals. So this is going to be, just plug it into the top one. We have 2 times x, which we found is negative 3, minus y, plus 3 times z, which we found was 5, equals 7. And now we just solve. Negative 6 minus y plus 15 equals 7. Negative 6 and 15 is 9. Subtract 9 from both sides. You get negative y equals negative 2, which means y is equal to 2. And so our solution is in order triple. We put it in order, so x is negative 3, y is 2, and z is 5. So those 3 equations with 3 variables can take some time, but just what you can do, again, take 2 pairs of equations, eliminate the same variable. So in our case, we eliminated y both times. Once you do that, you have those highlighted ones that I have there, and you can solve that system. And then once you find the two there, you can find the last one. All right, this last one, this is the one that's new to us. This, we have two equations with three variables. So we are not going to be able to find a exact solution, just one solution, but we're going to find many solutions. Actually, in this case, this is two planes that intersect, and they'll intersect in a line, but we're going to find an equation or a solution that gives us general solutions. And then we could find a specific one if we want to. So let's start working through this. You actually start off by eliminating one of the variables. All right, so we have two equations with three variables. We're going to go ahead and try to eliminate one of them. So the easiest thing to do is eliminate x, I believe, because we can multiply the top equation by -3, and that will eliminate the x's. So we have -6x minus 9y plus 21z equals -24. So we multiply the top by -3, the bottom we can keep the same, and that will eliminate the x's for us. So let's go ahead and add those. That's gone. We have -y plus 10z equals -20. All right, now what you want to do is you want to solve for the easiest variable to solve for. There's not always an easier, so you just choose one. In this case, it's definitely easier to solve for y. So we're going to go ahead and solve for y, which means we can subtract 10z from both sides. And we end up with -y equals, you don't have to do this, but I'm kind of putting it so it looks like slope-intercept form, but again, you do not have to do that. It's not needed here. And then we'll divide both sides by -1, which is really going to be just the same as changing all the signs. So we get y equals 10z plus 20. All right, now what we do is we are going to assign a different variable for z, which is the one that we didn't solve for. Okay, so we solved for y. So actually we eliminated x, then we solved what we had left for y, and we're going to assign a variable for z. Because what we're going to do is we're going to get a solution in terms of this other variable. You don't have to, you can do everything in terms of z, but we'd rather not. We want to use a different variable. So we're going to let t equal z. All right, let t equal z. So our answer will be in terms of t. And so our easiest ones, we found that, or we're saying that z equals t, or t equals z. We're now going to plug that, not that actually, we're going to plug t in for z. And so we see that y is going to be 10t plus 20. And we can take, once again, we'll take t and plug it in for z into one of our originals. It doesn't really matter which one. And we'll plug 10t plus 20 into our original. So we're going to take t and plug it in for z right here. And we're going to take 10t plus 20 and plug it in for y. And at the end, I'll explain this a little bit more. So now we have 2x plus 3y, but what was y equal to? It's equal to 10t plus 20. and then minus 7z. So minus 7. What was z equal to? Well, z was equal to t is equal to 8. So again, what we did was we took this first equation and put in what we found for z and y, and now we're going to solve for x. So to solve for x, we need to distribute. We have 2x plus 30t plus 60 minus 7t is equal to 8. We're going to solve for x. Add these together. You get 23t plus 60 equals 8. And we're going to go ahead and we're solving for x. So we're going to subtract 23t. We're going to subtract 60. So we have 2x equals negative 23t minus 52, because 8 and negative 60 is negative 52. And we're going to divide both sides by 2. And we get x. You can write this a couple of different ways. I'm going to go ahead and put the 2 as a common denominator. So x is negative 23 halves t minus 52 over 2 is 26. So our general solution in terms of t is x, y, z. Well, x is this negative 23 over 2t minus 26. Our y is 10t plus 20, and z is t. Now, what this means is I can pick any real number for t, any real number. I can pick 0, 1, pi, negative 60, whatever I want for t, and that will give me a specific solution. Now, there's an infinite number of solutions that will give me a specific solution. The easiest, so let me write this as a general, and actually there's a few general solutions, which I'll explain here in a minute. That's a general solution. To find specific solutions, and how many specific solutions can we find again? We can find an infinite number, and we do that by just plugging in a real number for t. So the easiest is to let t equal 0. So if t equals 0, a specific solution, so you're just going to plug in 0 for t, would be negative 26, 20, and 0. You could let t equal 2. That would give us another specific solution. If you plug in 2, the 2, I'll show you, we're going to plug in 2, so we're going to put t equals 2 for each value. So there's our x value, 10 times 2 plus 20, that's going to be our y value, and then plug in 2 for t there. And so that solution, it's going to be negative 49, 40, 2. Now there's a lot of room for error here with all this substitution or elimination and adding and subtracting. But what should happen here is any of these solutions these specific ones, we should be able to plug them back into both equations. So let's go ahead and check this. A little bit nervous here. Hoping I didn't make any mistakes along the way. And there's really no one here to point out any mistakes I made. So 3 times y, and then minus 7 times 0. So what I'm doing is I'm plugging in our ordered triple that's highlighted down there at the bottom into the first equation, and we're checking, does that equal 8? So we have 2 times negative 26 is negative 52 plus 60 minus 0 equals 8. And that is true because this is, we have 8 equals 8. So it worked for the first one. It also has to work for the second one. So 6 times negative 26 plus 8. So again, I'm putting in negative 26, 20, and 0. And for x, y, and z, 8 times 20 minus 11 times 0 equals 4. Again, that's plugging into the second equation. 6 times negative 26 is negative 162. No, negative 156. 8 times 20 is 160 minus 0. And that, in fact, also works. These equal 4. So there's a specific solution. Here's a general solution. Now, I told you I would explain this later. You can have other general solutions. So it depends on what you eliminate first. If we would have taken our original equations and eliminated z first, that would have given us a different looking general solution. Would it still have been able to get all, would it have been correct? Yes, it would have been correct, but it would just look different. So there you have it. That was new. We solved 2 equations with 3 variables. Again, the steps were we eliminated one of the variables. So I'll highlight this as we go along. We eliminated one of the variables. So we eliminated x. We solved for one of the variables. So once we eliminated x, we solved for one of the variables, we solved for y. And then we let t equal the one that we didn't solve for. So we solved for y, and then we plug t in for z, and then we use that to find y and x. And that is how you can find the general solution and specific solutions of 2 equations with 3 variables.